Happy viewers. In this video, we are going to discuss energy principles in structural analysis, which forms a powerful alternative to equilibrium-based methods. So far, we have used force methods like shear force, bending moment, and equilibrium equations. Energy methods goes one step deeper. They relate load, deformation, and internal energy stored in the structures. Foundation concepts. This lecture is built on the four foundation concepts. First, the strain energy fundamentals. In this, how energy is stored when the member is deformed will be discussed. And second, virtual work methods, which connects the external works to the internal deformations. And third, the energy theorems, such as Castigliono's and Maxwell's theorems, which are widely used in the analysis. And finally, the practical applications of energy methods, especially calculating the deflections in beams and trusses. Remember, whenever the force methods becomes lengthy, energy methods simplifies the problems. Energy principles, why it is important? Energy principles allows us to analyze the structural behavior as a whole, not just as an individual sections. They are particularly effective for long span structures, stresses with many members, and indeterminate systems. Instead of finding reactions and internal forces everywhere, we focus on the energy that is stored due to the deformations. Basic definitions of strain energy. Now let us define the strain energy. Strain energy is the internal energy stored in the body due to deformations. In simple terms, when an external load does works on the structures, the work is stored in the strain energy. As long as the material remains within the elastic limit, this energy is completely recoverable when the load is removed. Mathematically, strain energy is mentioned in the letter capital U, which is equal to work done by the load. This is the key assumptions behind all the energy methods. Strain energy density. Strain energy density is the strain energy per unit volume. For axial loading, it has been given by U equal to sigma square by 2E. Why it is important? Since it allows all the compare different materials, it plays a vital role in failure theories, and it helps define material properties like resilience and toughness. So the strain energy is associated with different forms of the stresses. So the types of the stresses are direct stress, shear stress, bending stress, and torsional stress. Strain energy concepts is useful to calculate the deflections of structures, and it has been denoted by the letter, as I already said, U, and U equal to half of P into delta. Modulus of resilience and toughness. Two important material properties arise from the strain energy concepts. First, modulus of resilience. It is the strain energy density up to the yield point. It represents the material's ability to absorb energy elastically. Second, modulus of toughness. It is the total strain energy density up to the fracture. It represents the material capacity to absorb energy before failure. In simple words, resilience will be equal to elastic behavior and toughness equal to total energy absorptions. So, resilience can be said as U equal to sigma square y divided by 2E, that is up to the yield point, whereas toughness can be given as strain of 1 will be equal to the resilience of the strain energy. So you can able to see in these equations, that is, if the stresses remains within the proportional limit, we can get U equal to sigma 1 square divided by 2E, and for the modulus of resilience, Uy equal to sigma y square divided by 2E, it is up to the yield point. Now we can able to see the strain energy in different loading conditions. So the strain energy under axial loading. For a member under axial tension or compression, strain energy is expressed as U equal to P square L divided by 2AE, where P is the axial load, L is the length, A is the cross-sectional area, and E is the Young's modulus. This formula is frequently used in trusses, axial bars, and tie members. Strain energy due to shear, bending, and torsion has been given as the following formula. That is, for bending, U equal to m square divided by 2 ei, and for torsion u equal to t square divided by 2 gj into dx, and for shear u equal to q square l divided by 2 ag, where m is the bending moment, t is the torque, I is the moment of inertia, j is the polar modulus, and g equal to shear modulus. These expressions are essential when computing the deflections using the energy theorems. Principles of virtual work. Now we come to the very powerful concept, that is principles of virtual work. It states that for a structure in equilibrium, the external virtual work equals to the internal virtual work. A virtual displacement is imaginary, very small, consistent with boundary conditions. This principle forms the foundations for many displacement methods. So, virtual displacement and virtual force method are the basics of principles of virtual work. In virtual displacement method, we apply the virtual displacement usually mainly to find the forces. It has been given by the expression as summation of pi into delta I is equal to summation of integral of m divided by ei into small m into dx. And in virtual force method, we apply a unit virtual force which is used to find the displacements. Delta is equal to summation of integral of capital M into small m divided by EA into delta x. The biggest advantages is we do not need complete force analysis, only the relevant terms is essential to find the virtual displacement and virtual force method. So the major energy theorems are Castiglione's theorems. So in Castiglione's first theorem states that the partial derivative of strain energy with respect to the load gives the displacement in the directions of the load. Mathematically, delta equal to dou u by dou p. This theorem is extremely useful for beams, trusses, and indeterminate structures. You will use this theorem extensively in numerical problems. Castiglione's second theorem. The second theorem states that the partial derivative of the complementary energy with respect to the displacement gives the corresponding force. This is particularly helpful in indeterminate structures where forces are unknowns but displacements are constraints. We can given as an equation as Pa equal to dou u by dou delta I. Maxwell theorem. Maxwell's reciprocal theorem states that the displacement at point A due to unit load at B is equal to the displacement at point B due to unit load at A. It given mathematically as delta AB will be equal to delta of BA. That is, displacement of A due to unit load at B will be equal to displacement of B due to unit load at A. This theorem is very useful in checking the results, influencing line constructions, and understanding structure symmetry. Yanger's theorems. Yanger's theorem is based on the minimum complementary energy. It states that among all the statically admissible force system, the actual system minimizes the complementary energy. This theorem is mainly used in indeterminate structures and redundancy analysis. So the applications of strain energies in beams and truss. Energy principles are widely applied in deflections of beams, slope calculations, joint displacements in trusses, and analysis of long span structures. In many cases, energy methods are simpler and more elegant than the force method.